So 2.7 is all about linear regression. For the past couple of days, we've been writing linear equations. We wrote linear equations on Wednesday, and then yesterday we wrote special types of equations, proportional equations. And in those two situations, we were sort of like making an assumption. We were making an assumption that the world is perfect and everything lines up neatly and nicely. But in the so-called, quote, real world, when you actually go out and get data, it's very rare, I would probably say near impossible, to find data that fits a perfect line. So it's actually quite difficult to come up with a single linear equation that accurately describes the relationship between two quantities. So instead of finding a linear equation, we instead look for correlation. So correlation is something we examine when it comes to real life data, because real life data is very ugly and messy. Correlation is the relationship or association, whatever word you want to use, between two variables. It is possible to talk about correlation between 3 variables, 4 variables, 5 variables, but then it requires like multi-dimension analysis, which will be on the scope of this course. So we'll just stick with 2 variables. When it comes to describing correlation, we typically focus on 3 aspects. The first aspect is the direction. Right? It's very normal to ask, hey, what is the direction of the correlation? Correlation, since we're talking about linear correlation, there are basically 3 responses you can give. Correlation can be positive. Right? So if you imagine a scatter plot, if you're plotting data, if you recognize that most of your points go up as you go right, we would say that this is a positive correlation. We could have negative correlation. So if you're making a scatter plot and you recognize that as you go rightwards, in general, you may have 1 or 2 that goes up, but in general, as you go rightwards, things tend to go downwards. We call that negative correlation. And you can simply have no correlation. These scatter plots look like you took, buckshot to a piece of paper. All scattered, random, no particular pattern, right? So when I ask you, hey, take a look at this relationship, what is this correlation? You could tell me it could be positive correlation, negative correlation, or no correlation. The next thing we sort of like to analyze or look at when it comes to correlation is his linearity. Linearity, the root word linear, it is what it sounds like. How much of a line is it? It could be yes or no. So this is more of a yes, no thing. So for example, this would have linearity versus something that looks like this. It looks like it's going to be linear, but then it sort of curls and plateaus. So the right one, I would say, does not have linearity, whereas the left one does. And the last thing we sort of look at or consider when it comes to correlation is the strength of the correlation. How strong is the correlation? And we typically have 3 categories. Correlation can be considered, strong. These are scatter plots that are tightly woven together. I would say that this is a strong correlation. You have moderate. These are ones that are more spread out. right? It's linear. You can tell it's linear, but they're looser. You could go down many avenues. And then weak. Weak, again, sort of just like no correlation. It looks like you just took buckshot to a piece of paper. But there is, if you squinted your eyes enough, if you wear glasses, if you take off your glasses and squint your eyes, it's sort of maybe okay, has some linearity, but it's very, very loose. Now, if you were to take a statistics class or maybe an AP stats class or a college statistics class, there is a mathematical way of describing the strength. We can do equations and formulas. But for our class, Algebra 2, we're just going to base it purely on visuals. Does it look close enough? Does it look close together, strong? Does it look pretty loose, moderate, or weak? I'm not going to be too picky about the strength here. When it comes to data collection, data analysis, it is possible to get these things called outliers. Right. These are data points, bless you, that are collected but do not exhibit the trend of the other data. Outliers can exist for various reasons. Maybe your data collection method was faulty and you got some bad data. Or perhaps it's just a very extreme, unique case. Whether or not we include outliers is completely dependent on the study you're trying to do or dependent on your threshold of tolerance. But visually, again, we're just going to do things on a visual basis. Visually, it's very easy to spot an outlier. So, for example here, if you had something like this, let's say we collected some data, we got this data here. Oh, we can sort of guess what's going on. But you know what? One of this data is all the way over here, and then one of this data is all the way down here. I personally, just on a purely visual, again, this is Algebra 2, we're not doing heavy stats, but just on a purely visual inspection, I would consider this an outlier. Because the general trend is down and to the right, and this guy's way up there, so something wicked happened there. Maybe my instruments were faulty, maybe I didn't measure things correctly, or maybe he's just that extreme, but I consider him an outlier. This guy down here, though, I would not consider an outlier. Although he is far away from his buddies, he does sort of exhibit the trend of the rest of the data points going down and to the right. So just because a data point is far away doesn't necessarily mean he's an outlier as long as he follows the trend. Does that make sense? All right. Now, how can I tell? How can I tell if I have strong correlation, weak correlation, if I have outliers or not? Like I said, we're doing everything purely on a visual basis. Well, to do a visual basis, we need a graph. A scatter graph, to be precise. I'm hoping this is a review. I mean, you guys should have done scatter graphs in like pre-algebra, but just to refresh our memories. Sketching scatter plots or scatter graphs. What you want to do is plot all of your data like normal. Right. Just graph normal XY points. And this is the next bullet point is sort of a Mr. Vo thing. Not many people do this, but I sort of like to do this. I like to plot what I call the mean point. Now, he's not a mean point because he's a jerk, but that just means the average point. Take the average of the x, plot it with the average of the y. And then just sketch or draw your line of best fit. Everyone's line of best fit will be different, and that's okay. But I try to equalize things. Have enough points above it, have enough points below it, but I always go through the mean point. So let's do an example here. Let's suppose you were, I don't know, doing a report on our school's athletic program. Yeah, that's going to be a positive report, I'm sure. And you wanted to see if there's a correlation between the ages of the students and how far they can throw, I don't know, a shot put, a football, a baseball, whatever you want to do it. And then this is your data that you collected, right? So you collected people's ages in years, and you collected the distance that they threw. And since you're being all scientific, we use the metric system, meters. So the data that you collected there was a 12-year-old who threw 20 meters, a 16-year-old who threw 35 meters, another 16-year-old who threw 23 meters, an 18-year-old who threw 38 meters, 13-year-old, 27 meters, a super senior 19-year-old, 47 meters, a prodigy, he's 11 years old. He made the team. Who doesn't at ASU Prep? 18-year-old. We're desperate for players. A 10-year-old. 15. This guy lied on his papers. A 20-year-old. Through 50 meters. 17. Big team. 33. Two more points. 15 through 22. And 13 through 20 meters. So, hey, we're desperate for players. We accepted this 20-year-old and a 10-year-old. So you can make like a double bar, just do another row below it. So to make a scatter plot, all it is just graphing points. If you know how to graph points, you know how to graph a scatter plot. But the first thing I like to do is I like to calculate the mean point. So the mean point is just the average of the x, comma, average of the y. In math, a vertical bar symbol just means average, or excuse me, horizontal bar means average. I hope we all know how to calculate average. Add them up and divide by however many numbers you have. So in this case here, I'll just take out a calculator. 12 plus 16 plus 16 plus 18 plus 13 plus 19 plus 11 plus 10 plus 20, 17, 15, 13. And you're dividing it by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 people. So it's about, I guess I should use squiggles. It's about 14.2, comma, 20 plus 35 plus 23 plus 38 plus 27 plus 47 plus 18 plus 15, 50, 33, 22, 20, divided by how many did I say? 12? 12. Oh, 29 exact. Right. So what you do is just go ahead and plot them. But, question?
For the mean point and average, you have to use squiggly lines.
Well, I only use squiggly lines. The question was, do you have to use squiggly lines? I only use squiggly lines because this came out to be a long decimal, so I'm rounding. So it's, if I were to say it equals exactly 14.2, that's a false statement. Am I going to deduct points if you do this? No. It's just know it's not going to be accurate. Right. When it comes to sketching, do some pre-planning. Take a look at your numbers here. So I see that the ages, the lowest is 10 and the highest is 20. So I don't know. Maybe I'll do it by 2. Each tick mark is 2 instead of 1. For the distance, the lowest is 15. The biggest is 50. Wow, that's a really big gap. So maybe, I don't know, by 5s. Does that sound pretty normal? So, I mean, there's no right or wrong way to do this. It all depends on how much space you have. But try to make life easy on yourself. Pre-plan things out and go with it. Oops, I don't want it upside down. Let's delete this guy. I'm only going to draw the first quadrant because I know all my numbers are positive. And as I said, we'll just do tick marks of 2. And that means I would need 10 tick marks. I think I can fit that. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And then we're doing tick marks of 5, so I need 10 as well. Hey, what do you know? 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. And then all I got to do is plots. Now, I'm not going to be, when I grade this on the quiz or something, I'm not going to be breaking out a ruler and measuring. Just do your best guess. 14, 16, 18, 20, 10, 15, 20, 25, 30, 35, 40, 45, 50. 12 and 20, somewhere right there. 16 and 35, right there. 16 and 23, so somewhere in between, right there. 18 and 38, so a little bit higher, closer to 40. 13 and 27, in between 27 is, I'm going to guess right there. 19 and 47, I'm going to guess somewhere right there. 11 and 18, somewhere right there. 10 and 15, somewhere right there. 20 and 50, somewhere right there. 17 and 33, 15 and 22, and 13 and 20. I'll go ahead and plot my mean point, and just to make it stand out, I'll do a different color. 14.2 and 29 is, I'm going to guess somewhere right there. Why is that the mean point? Is because it is the coordinates made from the averages of the x, comma, and the averages of the y. So it literally is the points of the averages. Yep. And then to make your line of best fit, just break out a straight edge. And again, everyone's line of best fit will be different. I like to go through the mean point, and I try to balance the points if possible. So I don't know, maybe that looks like my line of best fit. Those points on the bottom really mess things up a bit for me, but that's okay. That's what life is. Life is not perfect. So I don't know, something like that maybe. There is my line of best fit. And once you have a line of best fit, I can ask you all sorts of equations. I can ask you, hey, what is the equation in the line of best fit? Well, we just did that. All you have to do is find 2 points on the line, approximate it, and write the equation. I could ask you to make prediction. Hey, use your line of best fit to predict how far a 25-year-old should throw. So you just look on your graph, 22, 24, 26, and go to where the age 25 is. So you can do a lot of things once you have your line of best fit. And on today's practice, that's what you'll be doing. You'll be given a set of data. You'll be asked to look at a scatter plot and the line of best fit, and then you'll just be answering questions about the situation. Easy peasy?
Yes.
All right. It's a lot of work though, right?
Yeah.
Thank goodness it's 2019 and we have technology. So on the practice, I'm going to have you do one by hand, but the rest of them we can use technology. If I was going to do scatter plots, I'd break out my graphing calculator. Now I know not everyone has a graphing calculator. If you do and you don't know how to use it, I will show you after the lesson. But for the most of us, I'm guessing we're going to use our laptops. Question?
Are you recording the whole time?
Yes. All right. So, if you were, who's going to watch this?
I do. I'm subscribed. Notifications on.
Who outside of this classroom is going to watch this?
My mom.
So, okay, for the record, ASU Prep has an awesome athletics program. Here we go. If you do not have a graphing calculator, I would recommend a program like Desmos. Desmos can go ahead. That's what I'm going to show you. So if you know how to plot things, just like tune out for 5 minutes. If you do not know how to use Desmos for scatter graphs, listen up. Now, fortunately, you guys have your laptops. You can follow along.
Oh wait. Grab it. You just plug it in. That's most.
So all I do is I just literally Google Desmos. That's going to be the first result. And once you get on the screen, start graphing. If at any time you ever want to do scatter plots, you're going to hit the plus symbol in the top left, and you're going to add a table. Right. Here's where you're going to input your x and y values. So let's do the same scatter plot, so we should know what the data is. So you should have the data in front of you. So I'll just go ahead and quickly add it together. When it comes to Desmos, when you hit enter, it's going to go downwards. So you're going to hit all the x's first, and then input all the y's second. So we have 12, 16. Yes. So when you go into Desmos, the question was, how did I get this table? You're going to hit this plus sign in the top left corner, and you're going to hit add table. Yep. And then just go ahead and input your data. So I'll go ahead and input the same data, the age and the distance data. So here we have 12, 16, 18. How about you guys tell me so I don't have to keep looking back? 13, 19, 11, 10, 20-year-old. Hey, he's a super senior. 17, 15, 13. And then just move over. Do the same thing for the Y's. 20, 35, 23, 38, 27, 47, 18, 15, 50, 33, 22, 20. So we're just going to input the data that they give us. And then when you exit out, you're probably going, where's my scatter plot? I don't see anything. Well, notice the Desmos will always start at the origin. Our numbers are pretty big. So all you have to just move the graph, zoom in, zoom out, and then you will see the scatter plot.
Look at that.
Now, I mean, compare the computers to what we did on paper. It's close. No, that's not bad. Now, I want Desmos to plot the line of best fit. Here's the cool thing. It will do that for you as well. So in Desmos, go ahead and go onto a new line and take a look at your table. Notice how the headings is x sub 1, y sub 1. You can't use regular x's and y's. You have to use those sub ones. So we're going to type on your keyboard equation of a line, y equals mx plus b, right? We're going to type in y sub 1. So to get the subscript, we're going to type in y sub 1. So in Desmos, oh, I don't like how it covers it up. Strat. Well, you guys can see my keyboard, right? So I typed in the y. To hit the subscript, you're going to have to hit the underscore. So you're going to have to hit shift, and then the dash will give you an underscore. And what that will do is it'll bring the blinky cursor down where you can write the number 1. The problem is when you type in the 1, you're still in the bottom there. So you have to hit the right arrow to go back up top. So I hit the right arrow. Now my blinky cursor is right in the normal position. Now you don't use equals. Every single time you want to do a regression, you have to use a tilde or that squiggle symbol. That's going to be in the top left corner by your number 1. So you're going to have to hit shift and that tilde symbol, and then mx plus b. So I'm going to type in an M, but instead of an X, you're going to write X subscript 1. Hit the right arrow to go back to the normal level, and then plus B.
Plus B?
Yeah. So notice what I typed in here. Y sub 1 tilde M X sub 1 plus B. What that tells Desmos is, hey, I want you to graph a line, but I want to use the data from X sub 1 and Y sub 1. So Desmos does it, and notice the parameters, the outputs. It says M equals this, Y equals that. Guess what? That is your equation. So if I asked you, hey, what is the equation of your line of best fit? You would say it's Y equals 3.29 minus 20.34. Okay.
I'm hitting the underscore button right in the mix. It's not letting me.
So you're hitting the underscore button and it's not bringing the blinky cursor down?
Wait.
It's not bringing the blinky cursor down?
I have a castle pictures. Me? No. Okay,
Because you're all on the bottom. Right here.
No, it went to 1. I look like one of the 3 blind mice. I feel like one of them too.
It's not that hot. Or you can hand draw it. Alrighty, guys, we're not done yet. One last thing here. One last thing to talk about. 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 How many things do we have to talk about? One last thing. If you notice in the output, it gives you a lot of stat stuff. R squared, E sub 1, R. When you go into higher level mathematics, that R squared will be an important number to you, but we're only going to focus on R. That is what we call a correlation coefficient. So back to our notes here. You know how I said at the very beginning when we judged the strength of correlation, it looks strong, it looks medium. It's sort of like, fortune telling. It's your guesswork. R is a mathematical measure of how linear or how close your data points are to the line of best fit. So the correlation coefficient, which the variable uses R, is a mathematical number that describes how close your data points are to the line of best fit. Closer to +1 or -1, it doesn't matter, is closer to a line. So if you had a data set that was a perfect line, you would have a perfect 1. So the closer you are to 1, the more correlation it is to the line of best fit. Closer to 0 is no correlation. Right? Now, what would you have to do if you were a student in high school in the early 2000s as I was? This is the formula to figure out the correlation coefficient. It is a fraction of the summation of x sub I minus x bar times y sub I minus y bar all over the square root of the summation of x sub I minus x bar squared times y sub I minus y bar squared. That is what I had to do by hand in high school. Fortunately, it's 2019. If I ever ask you, hey, find R, just use Desmos or your graphing calculator, right? So I'll go ahead and give you the formula just because it's so cool to write down. But I will not make you do it by hand. If I ever have to ask you to find R, you're going to use a calculator. You're going to use Desmos or whatever.
Very nice.
Yep.
Thank you very much.
So that's it. On the practice, I believe they're going to have you analyze various scatter plots, and they're going to say, hey, guess what R this is? Well, if you have a very data that looks very linear, obviously you're going to guess a big R. If you have data that's all scattered, you're going to guess a very small R. So that's sort of the idea there. Know what R is. It determines how close to a line your data is. Closer to 1, more of a line. Closer to 0, not a line. Alrighty? That's correlation. That is 2.7.